Today I'm going to talk to you guys about the origin of where V1 over T1 equaling V2 over T2 comes from. From an activity in class, everyone should have had a graph constructed on Desmos comparing volume and milliliters to temperature in degrees Celsius. From this graph, everyone should have had a slope, a y-intercept, and an x-intercept that was crucial to get. From this x-intercept, we got out a significant negative 273 degrees Celsius being the absolute temperature, and we read a historical reading on that as well. But today I'm going to talk to you guys about after Kelvin had shifted the graph 273 degrees on the x-axis to get his own scale starting at 0 on the x-axis, the relationships between them led to the V1 over T1 equals V2 over T2. Even though both graphs in Celsius and in Kelvin are linear graphs, when you compare two different data points on them to each other, the ratios do not reflect a similar pattern. So for instance, if I take the data point of 802 milliliters for every 614 degrees Celsius, and I compare that to 282 milliliters for 40 degrees Celsius versus the same 2 points with different values on the other Kelvin graph, the unique relationship comes out to be true only under one of these circumstances. So let me compare each data point to each other as a ratio. If you divide these two, and this should be on a handout or in your notebook also. So 1.31 milliliters for every degree Celsius is what that simplifies to. And if I do the other data point of 282 milliliters at 40 degrees Celsius, you guys should see that that's 7.05 milliliters for every degree Celsius. So even though it's a linear graph, the ratios are not equal to each other. And we talked in class about how the y-intercept and the x-intercept likely shift those relationships and make them look different at each individual data point. However, if you come over to the Kelvin graph and you do the same technique of comparing these two ratios to each other in these 2 points, there's a unique pattern that shows up. So if I take the 366.3 milliliters and compare it to the 200 degree Kelvin, we should get about 1.83 milliliters for every Kelvin. And now if I go down to the first point near the origin and take 91.57 milliliters for 50 Kelvin, it also comes out to 1.83 milliliters for every 1 Kelvin. So these two ratios, even though they're on a linear line, do not equal each other. They don't simplify to be the same, but yet after Kelvin slides the negative 273 degrees Celsius to his own 0 point, when you do the ratio at any spot on this graph, we end up with equal ratios, and that's what leads us to be able to use the V1 over T1 equaling V2 over T2. And that's what I'll show here with example 1 and example 2. In example 1, you guys can pause the video and try this on your own, and the same thing with pausing and trying example 2. Predict the initial volume for a balloon of helium if it was initially at 19 degrees Celsius, but later was at 8 liters of gas at 24 degrees Celsius. Now you guys have to remember this ratio and relationship down here is only true on the Kelvin graph. When temperature is in Kelvin, you must change all these to Kelvin. So off to the side somewhere, you guys need to do work to show your change. And we allow you to do a shortcut in class after conceptually talking to you guys about how the y equals mx plus b of Kelvin versus Celsius actually allows us just to add 273. (19°C) plus the 273 should come out to be 292 Kelvin. And then if I change the 24°C, that should come out to be about 297 Kelvin. Now I've got my temperatures changed to Kelvin. I can now plug them into the mathematical relationship we derived from the Kelvin graph and show all the algebra needed to isolate the variable. I already know it says in the beginning that it wants the initial volume, so that's going to be V1, and at the temperature of 292 Kelvin. And we're going to assume that 8 liters is the final state because it says later was at 8 liters. And then a final temperature of 297 Kelvin. Our goal is to get the variable by itself. Luckily for us, V1 is in a very desirable numerator position. So I'm going to simply unlock the V1 from the 292K through multiplying, since it's stuck as a ratio in the division. And I expect you guys to show the work that I'm modeling on screen on your own notes too. Since I just manipulated the left-hand side, the equations no longer equal to each other, so I have to manipulate it to the right-hand side as well. So I need to bring the 292 Kelvin and multiply it. Here the Kelvins cancel, and I'm going to do a simplification step of taking 8 times 292. And you should get 2,336 liters. The 297 is still left over with no units because they canceled. And then if you simplify it one more step, you should get approximately 7.87 liters for the initial volume. Now you can check to see if this makes sense by checking the change in temp. The change in temp has increased. So if it is in fact 7.87 liters in the initial state, our graph suggests that as temperature increases, the volume should increase. So as we go from 292 to 297, this suggests that we go from 7.87 all the way to 8 liters of gas. So that seems to be accurate. Pause the video again to check your work if you worked alongside me, or pause it and move on and try example 2. In example 2, we're going to try to solve for the initial temperature of the bicycle tire with 3.5 liters of air prior to riding it outside in the cold at 5°C and 3.3 liters of volume. You guys also need to make sure you pay attention. The degrees Celsius is the temperature given here, and that has to be changed again to Kelvin. So off to the side somewhere, you need to be making sure you work in your scratch work to show me adding 273. Alright, so now I have the initial volume of the tire, the estimated final volume of the tire, and the estimated final temperature outside when riding the bike. So for V1, I'm going to put in 3.5 liters. I don't know temperature initial, so that's my variable I'm going to try to isolate. And then in the final state, I've got 3.30 liters at 278 degrees Kelvin. So on this situation, the variable is in an undesirable spot in the denominator. So we're not looking for any tricks or shortcuts here. You're just going to use algebra to rearrange these items. A lot of people will try to multiply the left side by 3.5, but it won't cancel the 3.5. It'll literally multiply it and make it liters squared, which isn't really a thing. So really we need to look at moving and isolating the variable itself. So since the variable's in the denominator, I'm going to multiply a numerator version of T1 so that they cancel on the left, and I'm going to do it on the right to keep the equation reasonably equal to each other. Now that it's a little messy, I'm going to rewrite this and end up doing the reciprocal to free up the T1, because now the T1 is stuck to this ratio. But the left-hand side is starting to look a little bit cleaner now that it's isolated from the variable. So now that we've got the ratio stuck to the variable through multiplication, I want to see you guys do the reciprocal of this ratio by flipping it. And show me that work. This whole package cancels, and so does this one. Now T1 is freed up. But since we did the reciprocal on the right, we have to do it to the left. Sometimes I'll rewrite this so it's not so messy, but for the area that I have left to work, I'm going to go ahead and just do the reciprocal on the left-hand side as well. And now, like we've said in class, this starts to look like a unit multiplier with the 3.5 liters canceling the liters on the denominator of the ratio. And now I'm going to do a simplification step. Bring down T1, 278 times 3.5. You guys should be getting 973 Kelvin. But that 3.30 is still a part of the situation here. And then if you divide 973 Kelvin divided by 3.30, you guys should end up with a temperature of 295 Kelvin. And so you can check to see if this makes sense. So if T1 was 295 and it decreased to 278, we should see a volume decrease according to our pattern, our graph. When temperature decreases on the Kelvin graph, the volume should also decrease. And so the 3.5 liters ends up being 3.3 liters, so there's a decrease. So it must have cooled from the beginning to the end, and 295 is warmer than the 278, so it seems to make sense.